Thank you very much. It's a pleasure to be here and talk with this distinguished audience about potential solutions for energy challenges that we have in the world today. What I'm going to tell you today is really about changes that are going on now and really the future. Some of them are very near term, some of them are a little bit longer term, but they really revolve around the idea of chemists and physicists doing basic science and then building and standing on the shoulders of those giants that did basic science to understand how materials function so that we can build them into devices that become commercial items that make an impact on our global energy challenges for the future. And that's what I'm going to talk about today. So in this first slide, this was an article that was written in the Wall Street Journal some time ago, and not my opinion, but basically saying that we need to bring less power to the people. That's really the solution for our energy. And this particular journalist mentioned 10 ideas on how we might do that, and two of them I'm going to discuss with you today. One is about implementation of new solar energy methods with new materials, and then the impact of lighting and displays. We saw in the last talk, if you look at the impact on energy, you can see that residential, industry, and commercial properties and buildings use enormous amounts of energy. Most of that's light and heating, and some of these problems can be addressed through chemical sciences. So what I'm going to tell you about today is the impact of chemistry and nanoscience and materials in the area of three particular areas that I've been working in and others have been working on. One is in the area of organic light-emitting diodes, and these light-emitting diodes are essentially plastic materials that have been developed fairly recently, actually, and now televisions and mobile displays are being made out of these particular materials, and the next television that you will want to buy is going to be AMOLED, which is active matrix organic light-emitting diode televisions. And I'll show you some amazing pictures, but they use very little energy, a few volts to drive them. They're literally as thin as maybe 10 pieces of paper, and they're really dramatic. And so people have been talking about conductive polymers going to revolutionize the world, and everybody's saying, oh, that's nonsense. Well, the future is here, and this summer you will see those televisions being released, and they will make an impact on energy. The other one that's really not very far behind is the idea of using plastic materials that can be used for lighting. These are highly efficient materials that you can make thin film printed plastics. I'll show you some wonderful pictures. And I have a large number of slides, but most of them are pretty pictures that you can see the demonstration and prototypes of these materials. These are very efficient plastic thin film materials that are more efficient than incandescent light bulbs, as you can read in the slide. Also, solar cells can be made out of these materials, and we hope that in the future you'll be able to use them. Plastics could be coated on all the surfaces and gather the energy from very low lighting conditions and to harvest the photons that are in this room and in any room and on roofs and etc. In the future. But we have a ways to go in that one in particular. The impact of basic science, as you all may know, has had a tremendous impact. It's built the internet. I mean, as you may remember, people were just trying to figure out how to transfer big pieces of data when they were doing defense-related research. And so they developed this ARPANET, which led to the internet, which completely revolutionized the entire world. Modern imaging technologies came from basic nuclear research, which people sometimes say, why are we doing high energy research? It makes no sense whatsoever. Well, actually, MRI and all the sort of medical imaging techniques were born out of those basic scientific discoveries. And even more important, as one of the speakers said today, many times scientific discovery is completely by accident. And to do world-class science and to find those innovations is to look for those surprises and then explain them. And when you do that, then you find revolutionary discoveries come out of that. Well, I know my audience, as they say. There was this guy, Niels Bohr, who was a pretty important guy who developed atomic theory, a Danish scientist, University of Copenhagen, 1913. And this was a basic scientific discovery that maybe people thought was pretty profound, but they said, you know, what does that have to do with application? Well, I can tell you that people took advantage of understanding that, and Schrödinger and others developed quantum theory, which developed orbitals, and the chemical orbitals and the definition of those chemical orbitals and the understanding of those orbitals led to the ability to take organic molecules with these orbitals and get them to overlap in pancake structures and crystallize them. And this is a tetrathiafulvalene tetracyanoquinodimethane. It's a chemical structure that was discovered by Dwayne Cowan and Johns Hopkins in 1972, which really understood that when you crystallize these flat molecules with these orbitals, they can overlap to form conductors. And this was a profound discovery. This was my advisor, and it's a Danish scientist, Klaus Beckhardt, who was a postdoctoral prior to me being in that group. So this was a really amazing discovery and was one of the first organic materials that conduct electricity. And so the story I'm telling you is about basic science and how it leads to revolutionizing the world. Shortly after that, and I wish Klaus was here, this is the only time I've ever seen Klaus with a tie in my entire life. I have no idea why he is wearing a tie, but someone captured the moment in a photograph. So this was a fantastic picture I was able to find off the internet. What Klaus did very shortly after that was discovered, he was a professor at the University of Copenhagen and still is, discovered what are called the Beskar salts. And these are crystalline compounds that you can see the green things are these orbitals that overlap with each other, and it led to the first organic-based, carbon-based superconductor. And these were studied, and lots of basic science were done in these things. And actually, something that came out of this was the discovery of C60 was shortly after this. And the discovery of C60 was fully understood because of many great scientists, but Klaus and Dwayne Cowan did a lot of basic science that help us understand how C60 actually conducts. Again, the understanding of these materials was really revolutionary and important. In 1976, Alan McDermott discovered, and this was an accident. It was completely by accident. He was, Professor Shirakawa was a professor, a visiting professor at University of Pennsylvania. And later, Alan McDermott in the early, sort of mid-70s, went to visit Professor Shirakawa. And there was a Korean graduate student in Professor Shirakawa's lab. And they were making polyacetylene because they were trying to make plastics that conduct electricity, because they had these, you know, alternating double bonds, and they could get the orbitals all line up with each other. These clouds of orbitals can create a conductive pathway. And he saw this Korean graduate student, and he said, what is this you have in your flask? It's this golden film. And he said, that's polyacetylene. And he said, that's not polyacetylene. And they went and looked, and the Korean graduate student had made a miscalculation on the amount of catalyst to make the material, and had made this unknown form of polyacetylene that had never been discovered. And Alan McDermott is sort of a Thomas Edison type of scientist, and you know, very quickly said, this is very interesting, can I take this with me? And cut off the foil and snuck it on the airplane and came back and treated it with iodine and found the first conducting polymeric material ever. And then later was awarded the Nobel Prize for this, looking for surprises and explaining them. So with that, the problem with this is that these plastics, they're not stable, they don't dissolve. So there's no applications, but still it was an important scientific discovery. Later, in 1985, several groups discovered a way, by putting these R groups, alkyl groups, on these polythiophene, that you could make them soluble. And so that was really important to make processable plastics. But again, they weren't very conductive. And then we came along and discovered these regioregular polythiophenes, which really dramatically increased the electrical conductivity of the materials, and that led to the development of transistors, printed electronics, and solar cells. And so that was but we really stood on the back of giants with that discovery. The field has progressed enormously. In 1990, this is where we were. There was no such thing as a polymeric transistor. Polymeric light-emitting diodes, it's plastic materials you apply electricity to that light up, had been discovered, but just discovered. There were no solar cells. There was really no commercial activity going on in this area at all. If you look at printed electronics today, we have OLED televisions and displays that are now coming to market. Samsung and LG have both announced that they're going to sell televisions this year to next year. LG is investing $2.5 to $3 billion. OLED lighting, I'll show you prototypes that are on the way. Transistors are already being used. Regioregular polythiophene is printed on plastic and used in train tickets in Germany already. And then solar cells have a little bit of ways to go. So I'm going to go pretty fast through the rest of this talk to show you some interesting examples. So these organic semiconductors are important because you can print them. And the printing allows you for simple and inexpensive manufacturing. And shown on this slide are plastic solar cells that are printed on plastic. These are 2 millimeter thick 13-inch OLED televisions that have been made out of these materials and futuristic displays. And I'm going to cover these three topics: light-emitting diodes, solar cells, and transistors. The advantages of these materials is you take the plastic, you make an ink, you can print it. The printing that's shown here are the actual printing from poly-IC, spin out of Siemens, where they print these transistors made out of regioregular polythiophene. You can print these on any surface, and you can have electronics almost anywhere. So the first thing I want to tell you about is printable transistors. And basically the idea I've already told you is to take these alternating double bonds, you make a polymer and a plastic material that conducts. And on the bottom you see a cloud of electrons, orbitals that all line up and allow you to propagate charge. But understanding the basic science behind these things really is the key. So we made a material, I say like a Lego block, that is, the front of the molecule has a front and it has a back, and if you connect the front to the back, you make a nice material. In a Lego block, if you put the back to the back, it doesn't make a good structure. It's the same thing that we did. By doing that, you increase the electrical conductivity up to 10,000 times. And that was a really important thing that we did. And we made a synthesis, a way to doing this. But what was important, to make it on a large scale and in a cheap way. And the synthesis on the bottom that we discovered, you can do this at room temperature, so you can make this on a very large scale. So if you look at these things can be manufactured on now hundreds of kilograms at commercial cost. They're still very expensive. We're on that $1,000 a gram, or between $100 and $1,000 a gram, but we're still these are specialty chemicals that take very little for electronics. We have the scale, but we have to understand the basic science. So nanoscience is very important here. If you're looking at, these are actually polythiophene nanowires that are 30 nanometers wide. These are the width of those nanowires is the length of the polymer. We had no idea these even existed when we first started out, but we first ran into these when I was spending 3 months with Thomas Birnholm, and he discovered the first polythiophene nanowires. We had no idea what they were, and it took us a while to figure out what the structure was, but once we were able to figure out that structure, then we had a very good idea that those nanofibrils were the length of the polymer and stacked on top of themselves, making these nanofibrils. And by understanding that, we were able to understand the charge transport in these materials. And these nanofibrils, if you take an AFM image of them, as shown on the far left, you can see this cartoon that I have, and it helps us to understand how these things conduct electricity. And by understanding how they conduct electricity, it allows you to understand how to design solar cells and transistors and devices. And so this basic science is really critical. So these things I've already told you are being used. People are trying to get them cheap enough to make RFID tags. As they get cheaper and cheaper, we hope to see plastic tags on everything. OLEDs. You can make polymers that you apply electricity to, and they fluoresce. You can make red, blue, and green. If you make red, blue, and green, you can make a television. And that's what we have. This is an old slide that said performance is an issue. Performance has been solved in the last couple of years. You can do roll-to-roll screen printing, inkjet printing now. You can put these anywhere on anything. They have the possibility to do lighting and displays I've been talking about. And it's really interesting. If you look on the left is an LCD TV, and it has all of these things in it. And these new OLED televisions are really interesting because you eliminate so many of these layers, and you save enormous amount in the cost of producing these televisions. And so that's one of the reasons that people are very interested. How does it work? You have a polymer, you apply electricity to it, you generate a plus and a negative charge, and that plus and a negative charge is an excited state. That's called an exciton. And one way for it to release the energy is to give off light. And depending on the polymer that you can change, you can make red, blue, or green. And you can put these things all together and then make your red, blue, and green. You can make televisions. And so you can make, if you make them yellow, you can make yellow signs. If you make red, blue, and green, you can make televisions as shown on the top. This has progressed enormously. From 2002, you can only make sort of yellow displays, and then very rapid in 2004, prototype TVs were made, and then in 2007, Sony released the first display that was made out of all small molecules, and this is a fully printed display here. And then the next slide shows a Samsung television or this may be Panasonic, that is not a prototype, but one that was sold. What about the future? I mean, these are the televisions. You're going to buy one of those. They're going to be OLED. They use low energy, few volts. They're great. They're not like plasma. They're not heavy. But what about the future? What else can we see? What about displays? I don't know if you can see this, but that's somebody's hand behind a screen that you can see through completely. So OLED displays that are completely see-through. You're talking about telephones that are made of OLED that you can wrap around a flexible strap that you could wear on your arm as a bracelet. This is a pull-out Google. It's a see-through phone that would look like this, and then you'd toss it, and all the OLED displays would come up to be your phone that you could just put in your in a little small like a cigarette lighter or something in your phone. You can already buy this. This is a watch. It's made by Sony. It's a smartwatch that has music and all these things, and it has an OLED display on it. So you can print these on things that are flexible and small. I think it's going to completely revolutionize electronics. It's coming. It's coming. All the major manufacturers are working in this area. Lighting. If you had red, blue, and green, combine them in the right way, you can make white. Or if you have blue and orange, you can also make white. This is a GE has been working in this area to replace the incandescent light bulb. You can see see-through lighting. You can imagine your windows in your house that would be windows during the day, and at night they would be lights. The timeline is near. It's 12, 13, 14. It's coming. I'm going to show you, there's a lighting conference that just occurred a couple months ago, and these are photographs of all different kinds of lighting displays by Osram, Conoco, Minolta, Maternity, and you can just see Philips lighting, all made of plastic materials that can be printed. This is an automobile lighting display at the bottom by LG Chem, and you can make different colors. So that's lighting. There is a lot of money being put into this area, and it's coming. So with the last minute or so I have left, let me just tell you a little bit about solar cells. Well, you can print these and you combine them with C60. This is a plastic film, and if you shine light on it, you can make power. They're not terribly efficient, but one of the great things about them is they can be see-through, and you can make windows, coatings for windows, hopefully someday, that we could coat all the windows and absorb light and make power from those things. And so that's the holy grail for organic photovoltaics. We are right about the you can make about 6% module efficiencies in the lab. You can make 10%, but we have a ways to go. And the conversation has changed dramatically with the discovery of Marcellus Shale. People are a lot less interested in this kind of solar in the United States now because of the shale discovery. But nevertheless, off-grid applications are probably going to be there. Where are we now? There's 10% in Champion lab cells, about 7 years worth of lifetime. If you think of these as throwaway solar, it's really, really very interesting. The cost is high, but there's no real big manufacturing going on yet. It's only a few people that are doing manufacturing. I'm going to skip the science piece. It says how it works. Denmark is leading the way in this. Professor Frederick Krebs at Riso National Labs and DTU is really the leader in large-scale manufacturing of, these are polythiophene, regioregular polythiophene things. He's made these hats that they were distributed at Roskilde Music Festival and is using them in Africa. So he's a real pioneer. There's a company called MicroPrint, which is in Denmark, which is a really world-leading printing company for solar cells. The efficiencies aren't great, but it's a start, and we think that we can have ubiquitous solar everywhere. We're doing that at a company called Plextronics that I started. You can imagine these things being in displays to absorb light to make new displays. That's where they're likely to see their first entry points, sensors, things like that. So with that, I hope that you will have some glimpse at not only the little bit further future, but the very near future. And all of these things are low energy, they're made out of materials, and we stand on the back of basic science to get to these applications. So thank you very much for your attention.
Well, thank you very much. We already feel a little bit better. You have a question?
That's just a fascinating talk. I really enjoyed that. Now, talking about sustainability, when it comes to electronics, we always hear about these rare metals that are needed here and there, and they are of strategic importance to make electronic devices. Are you telling us now that that's going to go away, and we're pretty much going to be making all of these things from organic materials?
That's the hope and dream. I mean, you can make thiophene from corn, so maybe there's a tie-in we could talk about. But yeah, no, we think that these materials, if you look at the, this is a chart that shows the efficiency. This is an old chart. We're now at 10% in the efficiency. But if you look compared to silicon and things like that, we're still a ways off. But if we can get to 10% with 10-year lifetime, I think you'll see these things ubiquitously be everywhere. I don't want cadmium telluride on my roof. I have a PhD in chalcogen chemistry. I don't want CadTel on my roof. And I don't want SIGs with cadmium, indium, gallium selenide on my roof either. I mean, maybe you do. I don't. Silicon, amorphous silicon has some possibility, but plastics is, I have one word for you, plastics.
Well, I'll just say this is exactly the sort of innovation we need, and I was pointing out in my talk.
Yeah.
So it's
Exactly.
great talk.
Thank you.
Anybody else? One more? Yes, please.
Martin Vigil of DTU. Plastics is the future, my friend. I recall somebody said many years ago in the movie. And it still is. Thank you very much for a wonderful presentation with a background in plastics or polymers. I enjoyed it very much.
Thank you.
I'd like to address to you the issue of, you use the words discover and understand and basic science and the importance of basic science. Now, this is called the ATV, the Academy of the Technical Sciences. So what are the distinctions between basic science, technical science, natural science, and where is the role of the engineering in here? Can you elaborate? I think maybe you are an engineer by heart, maybe chemist by training. You've been moved in your research, away from basic science, understanding of how nature is constructed, and maybe understanding how things, to maybe more inventing with a focus things that can be manipulated and designed using the building blocks of nature. Could you please elaborate on the role of engineering and technical sciences relating to the word basic science?
Yes.
Thank you.
That's an excellent question. I think one of the things that, this is my opinion, and I don't mean to be terribly provocative, but I think there's a complete continuum between basic science, applied sciences, technical sciences. If you look at the basic sciences, there's no problem with doing basic science for curiosity-driven science. There's no problem with that at all, and I certainly support that in every sense of the word. But what's really interesting to me is that we as scientists and engineers have a toolbox, and we know how to do certain things and attack certain problems. And what I've learned I have 2 companies that I started, and I learned from that more than anything that industry has the most interesting problems. And often academics don't understand that some of the most interesting problems that are out there are owned by corporations. And so working on the applied sciences side, we can bring our toolbox to still do basic science, but have, in some sense, a big impact on, and also solving some of the world's most difficult problems. And so often we don't know, as basic scientists, what the problems are. And when we go and talk with our colleagues in industry, then we find out what those problems are, and sometimes those are absolutely fascinating in every way and really drive you to sort of do the whole continuum of interdisciplinary science and then bind with your colleagues to try to solve those problems.
Thank you very much.